Bismillah. Welcome to Think Math. What happens when a mathematical function breaks its own rules? Today we are looking at the existence of limits for piecewise functions. Before we dive into the examples, let's establish the four rules we'll use throughout this entire lesson. Rule number one, the most important one. The limit of f of x as x approaches a equals L if and only if left-hand limit and the right-hand limit both exist and are both equal to L. We write this formula as limit as f approaches a from the left equals limit as f approaches a from the right. Think of it as two cars driving toward the same intersection from opposite directions. The limit exists only if they arrive at exactly the same point. Rule number two. The function does not need to be defined at x equals a itself. What matters is that the function is defined on an open interval to the left of a and on an open interval to the right of a. The value at the point itself is irrelevant of the limit. Rule number three. If the left-hand limit does not equal the right-hand limit, the two-sided limit simply does not exist. This is no compromise rule. Rule number four. If the function follows the same rule on both sides of the point, we don't need to check left and right separately. We can evaluate the limit directly by substitution. Two more special cases to know. Rule number five, when the function contains an absolute value of a polynomial, that is y equals the absolute value of f of x, we can use direct substitution to find the limit. For example, if f of x equals the absolute value of x squared minus 4x plus 3, then the limit as x approaches 3 is simply the absolute value of 9 minus 12 plus 3, which equals 0. Rule number 6, endpoint behavior. When a function is defined only on an open or closed interval from a to b, something special happens at the two ends. At the left endpoint a, the function only exists to the right of a, so we can only discuss the right-hand limit. The left-hand limit and the two-sided limit do not exist here. At the right endpoint b, the function only exists to the left of b, so we can only discuss the right-hand limit. The left-hand limit and the two-sided limit do not exist here. In short, at terminal boundary points, only one-sided limits are possible. Keep that in mind as we work through the examples. Now let's put those rules into action. Our first function has two rules, 3x plus 1 when x is less than 1, 5 minus 2x when x is greater than 1. For part A, we want the limit as x approaches negative 2. So negative 2 is less than 1. We are on the left side of the boundary, so we use only the top rule. Direct substitution, 3 times negative 2 plus 1 equals negative 5. For part B, the limit as x approaches 3. Since 3 is greater than 1, we are on the right side, so we use only the bottom rule. 5 minus 2 times 3 equals negative 1. Now, part C, the interesting one. The limit as x approaches 1. This is exactly where the rule changes, so we must check both sides separately. Approaching from the left, we use the top rule. 3 times 1 plus 1 equals 4. Approaching from the right, 5 minus 2 times 1 equals 3. 4 does not equal 3. The two sides don't agree, so the limit as x approaches 1 does not exist. This is a classic jump discontinuity. Example 2. We have a polynomial piecewise function with a boundary at x equals negative 2. The left-hand limit uses the top rule, negative 2 squared plus 2 equals 6. The right-hand limit uses the bottom rule, 2 times negative 2 plus 3 equals negative 1. 6 does not equal negative 1, the limit does not exist. Example 3 introduces absolute values. F of x equals the absolute value of x minus 3 divided by x minus 3. To analyze this, we split the absolute value by definition. When x is greater than 3, the expression x minus 3 is positive. The absolute value doesn't change anything, so the fraction simplifies to exactly 1. When x is less than 3, the expression x minus 3 is negative. The absolute value flips the sign, giving us negative of x minus 3 in the numerator. The fraction simplifies to negative 1. Right-hand limit is 1, left-hand limit is -1. They don't match. The limit at x equals 3 does not exist. Example 4 has three rules. The two boundary points x equals -3 and x equals 5. First boundary, x equals -3. From the left, we use the first rule, 2 times -3 plus 9 equals 3. From the right, we use the middle rule, 3 times -3 plus 7 equals -2. 3 does not equal -2. The limit of x equals -3 does not exist. Second boundary, x equals 5. From the left, we use the middle rule, 3 times 5 plus 7 equals 22. From the right, we use the bottom rule, 5 minus 5 equals 0. 22 does not equal 0. The limit at x equals 5 does not exist either. Both boundary points fail the test. In example 5, we have a trigonometric piecewise function with a boundary at x equals 4. Left-hand limit, as x approaches 4 from the left, we have sine of x minus 4 over x minus 4. Let u equal x minus 4. As x approaches 4, u approaches 0. This becomes the standard limit of sine u over u as u approaches 0, which by our fundamental trigonometric limit rule equals exactly 1. Right-hand limit, we substitute x equals 4 directly into tangent of pi over 16 times x. This gives tangent of 4 pi over 16, which simplifies to tangent of pi over 4. And the tangent of pi over 4 is exactly 1. Left-hand limit 1, right-hand limit 1. They match perfectly. The limit of f of x as x approaches 4 exists and its value is 1. Example 6 works in reverse. We are told the limit exists and we must find an unknown constant a. The function is tangent of 4x times cosecant of 9x for x less than 0, and 1/9 times a squared plus 2 for x greater than 0. Left-hand limit, cosecant of 9x is the reciprocal of sine of 9x. So our expression becomes tangent of 4x over sine of 9x. Near x equals 0, tangent of 4x behaves like 4x, and sine of 9x behaves like 9x. So the ratio approaches 4x over 9x, which is 4 over 9. Since the limit exists, the right-hand limit must also equal 4 over 9. So we write a squared plus 2 all over 9 equals 4 over 9. Multiply both sides by 9, a squared plus 2 equals 4. Subtract 2, a squared equals 2. Take the square root, a equals positive or negative root 2. Before today's exercises, let's quickly review the answers to last lesson's quiz on trigonometric limits. Question 1. Sine of 3x squared times cosine of x squared over 5x squared. The cosine approaches 1, leaving us the coefficient ratio 3 over 5. Question 2. 2x minus 3 sine x over 3x plus tangent x. Near 0, numerator gives 2 minus 3. Denominator gives 3 plus 1. Result is -1 over 4. Question 3. Evaluates to 23. Expand the tangent squared term near 0 to verify. Question 4. Factor out 3 from sine and 3 times x minus 4. The standard form gives us 3. Question 5. 4x over sine 5x near 0 equals 4 over 5. Question 6. Using the standard cosine result near pi over 2, the answer is -1. How did you do? If you missed any, make sure to review the previous video. Now here are your 3 exercises. Pause the video and try each one. Exercise 1. Find the limit of the square root of x minus 3 as x approaches 3. Think carefully about the domain boundary. Which procedure applies here? Exercise 2. Find the limit as x approaches 0 for this piecewise function involving 2x over sine x and 2 cosine of 4/3 x. Exercise 3. Find the limit at x approaches 0 for the piecewise function involving these absolute value expressions. Write your answers in the comments. I read every single one. Thank you for watching. See you in the next lesson.